Welcome. This screencast corresponds to the first part of Topic 6. Topic 6 is all about kinetics and thermochemistry, and they present it, the Brown SL book presents it in one big section. And so I'm going to break it up into 4 smaller screencasts, and I'm going to assume you don't know anything about kinetics or energy and reactions. So the word kinetic comes from the Greek kinesis, meaning movement. And so in chemistry, we use kinetics to describe how fast a reaction goes, or reaction rate. And we use it in industry for safety. We also use it for efficiency. And probably most importantly to most companies is for profitability. How fast can you make your product? And knowing how quickly you can produce your product and under what conditions then allows you to maximize your safety, efficiency, and profitability. For example, you have to know what pollutants and toxins are produced and how quickly they're going to be produced and how you dispose of them. In pharmaceuticals, we want to know how quickly drugs can be released or how slowly over time, depending upon what they're doing. So there's all kinds of reasons for studying kinetics in reactions. So kinetics looks at reactions on the molecular level. So it looks at the bond breaking and then the bond making over a sequence of steps. Most reactions occur in a sequence of steps called the reaction mechanism. So you can actually look at a series of smaller reactions that, when you get all done, add up to the big reaction that we usually look at as our balanced equation. So collision theory is used to explain how different factors affect this reaction rate. So rates of reaction are generally measured in terms of time, but they're expressed as a rate, or they're expressed as per time. Okay, so rates are always compared to time. And so rate is the reciprocal of time, and as the amount of time increases, the overall rate always decreases. And it doesn't matter if you're looking at reactants consumed or products produced, the rate decreases over time. So it's just going to be a matter of whether you're measuring how quickly the reactants are being used up or how quickly the products are appearing, but either graph is going to have a decrease in slope over time. The graphs, however, are going to look opposite. Down below, if it's product, it starts at 0 and it quickly increases and then levels out over time. Whereas if it's reactant, it starts out high, quickly decreases over time, and then again levels out as you approach equilibrium. So looking at a graph, you should be able to tell if you're measuring product or reactant. Rates of reaction is defined as a measure of the amount of reactants being converted into products per unit amount of time. And again, so we do it either by measuring the reactants being lost or the products being gained. And it's expressed as a change in concentration per unit time, or moles per decimeter cubed per second. That's because you only look at one reactant or one product changing over time. So the equations are shown below that you can look at the change in concentration of product or the change in concentration of reactant. In either case, you divide by the change in time. The balanced chemical equation, just looking at it, tells you nothing about rate. You have to actually experimentally go in and measure what's happening with rate. A graph of concentration of either product or reactant over time will yield a slope equal to your reaction rate at any time. And again, we'll see that slope start out very quick and decrease over time for every reaction. So really, if you could find the slope at any single instant, that would be the rate for that exact point in the reaction. So again, rates of reaction are always going to be a curved graph, indicating that the rate doesn't stay constant. It's going to be steeper or faster initially and then slowing. Again, it's going to be a negative slope if reactants are being consumed, or positive if products are being made, but we always express the rate as a positive value. And I started speaking on the previous slide about something called the instantaneous reaction rate. If you want to know the reaction rate at a particular point, you can just look at the concentration of your reactant or product at that time. And to do that, what you do is you draw a tangent to the curve at the time you're interested in. So at 120 seconds, I drew a tangent to my curve and I extended it out each direction. And I saw at that instant, if I extend all the way to each axis, at 283 seconds, the concentration is 2.40 moles per liter. So I can go ahead and take that 240 moles per liter and divide by 283 seconds, and I have an instantaneous reaction of 8.48 times 10 to the minus third. Now you notice they expressed as a negative 2.4 because it's reactant, but rate should really be expressed as a positive here. Along with the instantaneous reaction rate, there's also something called the initial rate of reaction, and it's just what it says it is. It's the beginning or starting rate of reaction. So it should always be the fastest or greatest rate since all the reactant is present. So you have maximum number of collisions occurring then. So it's calculated at the tangent to t equals 0, and it's often used for comparison at a later time in the reaction. So if I look at my graph here, at t equals 0, 1.92 is my beginning concentration, and when I extend the slope down, that is time about 68, 69 seconds. And so I can go ahead and calculate my initial rate of reaction as 2.9 times 10 to the minus second. And then if I want to compare it to a later time, say at 90 seconds, I draw another tangent. I look at my concentration from that tangent is 1.18, and the time is up to 164 seconds. And now my rate is decreased to 7.2 times 10 to the minus third. And so this is really helpful. If I change a condition of the reaction, my initial rate should remain the same, but if I had a catalyst, I would want to see how differently my reactant is consumed. What would it be at that point? Or if I change the temperature. So the initial rate is going to be assumed to stay pretty constant when I change conditions, but it's as you go on in time that the effect of that factor is going to be seen or measurable.